So yeah. Good morning, good afternoon, and good evening, everyone, based on your respected time zones. Um, yeah, so I'll start because I have to cover a lot maybe today. If not, I'll drag it to the next class. Yeah.
Thank you, Manish, for considering this. I really appreciate that.
Yeah, thank you.
Yeah, thanks. Yeah.
So today we are going to learn how to build a complete computer vision workflow from scratch. Previously, we have seen projects on regression, time series, supervised, unsupervised, machine learning models, deep learning, and all. So this is a bit similar, but a new way of looking at AI. So till now we were only considering the brain part of the AI, but for once we never thought of the sensory organs of the AI. For example, like your eyes, for a baby, how eyes, ears, nose, they all work, right? The skin, the sense of touch and all. So the sensory part of the AI. So here comes, today we will be covering one of the sensory part of the AI, that is eyes. We are going to cover the eyes part of the child, and the eyes part is nothing but the computer vision, how computers look at the world, how they understand the world by just the images, videos, and all. For example, when there is a robot, and how the robot perceives the vision, the 3D environment around it, that is all we will be discussing today. The goal here is not only to understand the models. I'll talk about the models, like what is this Coco, YOLO, and all. The goal is not only to understand what the models do, but to understand the whole complete pipeline that makes the model useful. So you will be starting from scratch by getting the data sets, and we'll be building the entire pipeline, and we'll be deploying the models. Like it's a complete pipeline that we are going to see. Same like how we have seen for time series regressions and all. Here also we have a particular pipeline that we have to follow. And by this end of this class, you should be able to take a folder of images. You should be able to label them. You should be able to improve those labels, organize them for ML. So you will be able to do all of this. And also you also can do something called fine tuning a model on your own problems. Fine tuning, again, I'm saying it's not like there is no standard rule of fine tuning. This is one of the questions that was asked to me during the weekdays. One of our friend messaged me. So fine tuning, there is no particular rule that can be applied to all the concepts, all the use cases in the projects. Fine tuning is something that you have to figure out. It's like it's like you tweaking few things and checking if it is working for your use case or not. That is how fine tuning works. There is no particular set of parameters. There is no set of particular rules that you can follow in fine tuning. So fine tuning is different for every single use case. Yeah, and I know this is not there in our syllabus that I've designed in the initial thing, but one of our friend asked a very practical question. The question is, I remember the question still, like we have a set of images, and we can annotate those images like manually or automatically. We can do that. And we can improve the annotation is nothing but there are images and you naming that image. For example, in that image there is a cat and a dog. You are naming that this is a cat and that is a dog. This is called annotations. So how do we improve the annotations? Using images as features and annotations as targets, and then train and evaluate the model. Like is it possible to do all of this? The answer is yes to that. And that is exactly how real computer vision projects are also built, and we will be exploring all of that today. And what makes this especially exciting today is that we no longer need to label every image completely by hand. Previously, like take few years back, if you take any data set, you have to scientists, data scientists used to label the images by hand. I'm not joking. They used to drag boxes around the images and they used to write, this is cat, this is dog, this is human, this is a chair, this is a pen, this is a pencil. So they used to annotate the images. But in this time, we no need to do in such way, because there is something called grounding dyno. I'll talk about it later. Models like grounding dyno can detect objects from the text prompts. They can just automatically detect the objects from your images. And SAM2, I think I did not write. Oh yeah, here it is. SAM2. And SAM2 can turn prompts or boxes into segmentation masks. I'll talk about all of this in detail. Something called segmentation masks. So grounding dyno is designed as an open set detector that can detect arbitrary objects from human text input, and SAM2 extends the promptable segmentation to images and also videos with a strong zero shot performance. But I'll talk in detail. I'm just giving an overview of what we are going to see today. And yeah, so instead of thinking annotation as a boring manual task, think of it as a human in the loop workflow. The model gives us a draft and we will correct it. That is what happens today in these days. Earlier days, it is completely different. We used to have images and we used to label each image. If there are 1,000 cats, 1,000 times you have to write it is a cat. So it used to be very tough earlier, but now it is good. And grounding dyno and SAM2 are something they came out as a research from Meta, Facebook Meta, and they have revolutionized how computer vision works these days. This is a very latest technology. I don't think you will even find much content about these two in internet. They're pretty new. I think Meta, when they were developing the glasses, Meta glasses and the this thing, their AI world, sorry, not AI, their AR world, their augmented reality world with their goggles, AR goggles and all. At that time, they were researching, and these two came out of that. I think it's from a Meta team. Yeah. So before we start, you have to ask yourself the questions like, how do you perceive an image? How do you perceive the world? How do you are looking at this class and understanding the things? So these are the things that you have to ask yourself. Like, I'm talking more of a generalized way, like how you're looking at your monitor, how you're looking at your laptop. How do you know that you're looking at a laptop? You're looking at a squared some shape, right? How your mind knows that it is a laptop. So ask these kind of questions to yourself. And from a technical perspective, you can ask questions like, how many of you already have image data? How many of you have labeled data? How many of you have images but no annotations yet? So these are some of the questions that we delve into when we are going to technical side. And the same happens for the child as well. When the child was looking things for the first time, the child doesn't know anything. It's of a zero memory. So you, as parents tend to keep the data into the brain. For example, they show an apple. The child only sees that it is some form, it's some shape. It has some properties like red, round color and something like that. The parents gives the annotation. Here the annotations means the external data. They tell the child that so and so, which is round, red color, have a particular texture, is called apple. It is called apple. And they show ball, and they show different types of things, and they name them. In childhood, I still remember we used to have books, like a very colorful books. In like LKG or UKG books, if you take, their books will be filled so colorful. And the book doesn't do anything. It just shows the images and annotates what that image is. For example, that book will show like a cat image, and it will write down it is a cat, a dog image and dog, and a cricket bat image, and it names as cricket bat. some sport, and it will name as that sport name something. So image data, image data, image data, image data. That is how child learns in their earlier education days, like LKG or UKG. So that gets remembered, that gets annotated into their brain, and for the next time when they look at the similar kind of things, their brain tend to see if the similarities between the data annotation that they already had and the image, and they tend to identify the things. And the same goes here as well. So any doubts on what we are going to do today? And anyone? If any doubts, please let me know.
Monish, are we still doing it in the Colab or?
We will do it in Colab.
Okay.
Yeah. So this is how I divided the class into. We'll be talking about data sets and the setup, then the annotation part, then how we train and evaluate the models, and I'll talk about some end-to-end pipeline. I mean the same thing, end-to-end pipeline. Yeah, this is the pipeline. So this is any computer vision project follows these 5 steps. One is collecting the raw images, public data sets. But for our project that we are going to see, aquarium object detection, we'll be using a dataset from Kaggle. But in real life, I mean, my own brother, he's working as an OpenCV engineer. I've seen his work. So what happens is, like, in a real world scenario, the industry in which you are working, they will be providing you with lot of raw footage, raw video footage from the cameras. And you will be taking all those videos, you will be converting them into frames, like 60 seconds of 60 frames per second. You all know this, right? Each video will be playing in 60 fps, 30 fps. Some video cameras, CC cameras will be playing 30 fps. Some video cameras will be playing in 60 fps. You have to divide those frames, and you have to find the unique frames, and you have to convert them into raw images. And after converting into raw images, you have to use some algorithm to start the annotation, and then you'll be feeding it to the algorithm. So that is how their pipeline works. And one more thing, I'll be very honest, I've never got a chance to work in OpenCV in any direct companies. I never worked. But I did my own personal projects on OpenCV, like few detections and all with YOLO and YOLO 3. But I never worked in an industry standard. But I mean, whatever you're seeing here, all this information, I've gathered it from my one of my brother. But yeah, I have not really worked in the industry, but whoever is really working, I got the information from them. So first they collect the images. They take the raw, they take the footage, they convert into individual pictures, individual raw images, and then they have an archive mode. And in the archive mode, they will be storing all these images, and they'll be converting, they're putting the annotations on top of those images. They will annotate the images. Usually it used to be manual, it seems, like very few years back, even in the industries as well. But now it was completely LLM assisted or the algorithms assisted. They are not doing it manually. And after that, most of the times they will be correct. Whatever the annotations they have done, it will be correct. But there will be few scenarios where the annotations may go wrong. It's a very minor error rate, but still they have to consider it. And they will be reviewing the annotations, fixing the annotations, and they will be changing. If for example, there are some cases, and the most problematic, like there are some colors actually. That colors also causes a lot of issue in cameras. Like anything that you wear are reflective t-shirts or a reflective designed shirts or something like that. The labeling goes wrong. And any green color shirts or green color t-shirts or anything that is green also can sometime go mistake in annotating. So there will be some mistakes there, and they will be correcting those images. And finally, targets. So what is this features and targets is that what you are trying to look into, what your use case is. For example, in their industry, I mean in my brother's industry, they will be looking more into safety. For example, if anyone, I mean it's in what do we call steel melting kind of industry. What the 24/7 what is monitored is like for safety. If someone is wearing their safety hat or not, if someone is wearing the safety clothes or not, if someone is wearing safety boots or not, how the metal is moving, how the nuts, I mean the screws, how the screws are there. If anyone is walking down of the furnace, if anyone is walking near the furnace, these are the things their company is more into, the safety aspect of the industry. So there the features are like the safety boots, the safety material, the safety gear, person near the furnace. These are all the targets. External, all the things are features. The hat, human, furnace, these are all features. Targets are anyone if is nearing to furnace, then it is a target. Or if anyone not wearing a hat, then it is a target. So these are all the targets. By the use case, it differs again. And finally, we will train the model and we will evaluate the model if it is working or not. In this project, it is going to be more of static, but in real companies, the model will be running 24/7 in a server. So the CC camera will be taking the video. That video will be sent to the model. The model will, every second the model thinks if everything is going well or if something is going bad. If something is going bad, immediately the safety team will get an alert. That is how they design the system. So video 24/7 there will be video capture. Even in the nights there will be video capture. That videos will be in a pipeline. That video will be sent to the model. I mean, sorry, the video will be converted to image format, and that images will be going to the model. The model then identifies if the image is looking good or bad. If it is bad, an alarm will be raised. So this is how the pipeline looks like. Any doubts in this pipeline? Anyone? Again, just one more time I'm repeating before going into the next slide. First we collect images, next we annotate them. This is used to take weeks before, but we will, nowadays everyone uses AI assisting tools to annotate them. Then they refine the labels. No automated system is perfect, so human review is crucial in this step. And then fourth, they structure the data into features and targets, image mapped to their bounding boxes. And then finally, they train and evaluate the model. So keep this pipeline in the mind. It will be our compass. This is going to be our compass moving forward. Data sets and setup. Yeah. So how do I start? At its core of a CV dataset of a computer vision, CV means computer vision dataset, it is divided into two parts. Every dataset you take, it is always divided into two parts. One is features and the other is targets. You can even right now, you can take a pause, go to Kaggle, look for any computer vision dataset. You will find these two differences. One is images, one is the annotations. I think in one of the class I showed you also, like we have taken a cat and a dog, and I've shown you how the labeling separates from the images. Did I show it to you in this class? I don't remember.
I know in the previous class I have learned that in the earlier class.
We did, right? With
I don't know about in this course, but I know in the previous course I did learn that.
Okay.
Yeah.
Let me open. Sorry. Open notebook. Not movie. NLP movie, deep learning, unsupervised. I think in unsupervised class I've taken it. No, not unsupervised also. Netflix, Transformers. Deep learning. Maybe what did I deep learning basics? Yeah, we used vision here. Yeah, in deep learning, I've shown you some data set for t-shirts and all for fashion. Even in that data set also, class target will be different. I mean, all the images are collected separately and the labeling is collected separately. Just an example. And we have used a gist of computer vision in this class to understand the images. Yeah, but we have dealt more into deep learning in this class, but this also can be a computer vision project if you ask me. Yeah, something like this that we have done. So yeah, so every data set will be divided into two parts. One is the images features part and the other is the targets part. The features are your images. These are your raw pixels, like it can be in JPEG format, PNG format, TIFF format, or any of the other formats. They carry metadata like resolution, bit depth, channels, how many colors are used. All of that are carried by the image. Every image will have a metadata. Every image, any social media image also you take, there will be some or the other kind of metadata that is embedded into the image. And there is one time, I think in World War II or something, they used to even they used to communicate using these images. Images would be sent from one place to another place, and scientists of the other place used to decode that image into metadata. Metadata can be placed into an image. So it also carries metadata like resolution, channels, bit depth, color depth, and all. And yeah, in a typical project, you will split these images into 70% for training, 15% for validation, 15% for testing. Not the 80-20 rule. Remember, for a typical CV project, usually 70% goes for the training set, 15% goes for the validation set, 15% goes for the testing set. This validation part is something new to you. We have seen in deep learning project also, but in other use cases like supervised, unsupervised, you wouldn't have seen this. Why? Because in numbers, if you're dealing with numbers, 80% training, 20% testing will be more than enough. But coming to images, there is a lot of ambiguity for the images. Images can be of different angles, different shapes, different colors, and all. So always validation is recommended. So what do we take? After the training, once again we will validate them. In the validation, if something goes wrong, again you can do the training. So that is why validation is used as a bridge between testing and training in OpenCV projects. And usually OpenCV projects are one of the most crucial projects. Why I say? Because cancer treatments, surgical projects, like any projects that is related to surgeries, theft, robbery attempts, or safety protocols, or any assault on public areas or any private areas, any use case you take, they all seem to be very emergency situations. If you think for a second, all the OpenCV use cases that you take, most of them, I would not say all, most of them, they all delve into emergency situations. Like then and there we have to get a response, then and there someone has to do something. It is not like this happens now and after 2 months you can take care of it. That doesn't work like that. OpenCV projects is one of those kind of projects. It needs lot of detailed work to be happen. I mean, it has to be more precise, is what I'm trying to say, because even if one pixel is differed, even if one pixel calculation goes wrong in OpenCV projects, your entire thing can be, the emergency situation can be gone wrong. For example, what I can say is, uh, yeah, this happened. I mean, again, this is what when I was talking with my brother regarding this OpenCV, this is one of the example he gave me. I was trying to recollect what exactly he said. So one guy, what he did is, instead of wearing his safety gear, he was wearing a similar color. They wear actually yellow color helmets. So similar yellow color hat. He was wearing a leather hat, not his safety yellow color gear hat. So actually, what should happen is, it should get off of alarm. Like all the safety management people, they should get an alarm that so and so guy is not wearing the hat. But no alarm was raised. And later, like 3 or 4 days after, when they were the CCTV camera guy, when he was checking it, then he observed it, why there was no alarm. Then they looked at the model, then they looked at the images, everything. They found out that since it is same yellow color and the shape also looks the same, the model thought that it is a hat, and it did not raise any alarm. So these kind of things happen in OpenCV projects. The same can happen in during cancer identification treatments or surgical treatments and all. Even in army also, OpenCV is used a lot. So precisability is one of the most important factor in OpenCV projects. So that is why we also do validation before going to testing. And the targets are your annotations. The targets are your actual annotations. These tell the model what to look for, whether that bounding boxes for object detection, segmentation marks for precise pixel outlines, simple classification labels, all this comes under targets. Like what that image is. Like that image can have 10 different things. All the 10 different things will be labeled. This is called annotations. So this is how the data set is divided. And your model will only ever be as good as your annotations. If your annotations are bad, your model will be bad. If you are doing specialized scientific work, 1,000 perfectly annotated images will easily outperform 1 lakh noisy sloppy ones. Remember that. That's why I have added this line. 1,000 well written annotated images are more better than 1 lakh noisy ones, bad ones. One more if you still did not get what is an image and an annotations are, I can simply give you an example. My monitor turned off. Yeah, I'm resharing. So yeah, my monitor is turning off during the class. I'll tell you the reason also. It's because my monitor's FPS, the my monitor's FPS and the screen recording that I'm doing, they're not matching. So there was a flickering happening sometimes. You cannot see that, but I'm seeing from my side. Since they both are not matching exactly, there was a small flickering, and during the flickering I'm just turning off the monitor and turning it back. That is fixing it. Where am I? Yeah, I'm showing you an example. Images versus annotations. Yeah, so you take this image, right? This image without this yellow box and the red box is a feature. It is a feature. The image itself is a feature. The yellow box, the red boxes that you see, these are called annotations. These are called annotations. So that is the difference between a feature and an annotation. When you bring them together, then you will have this particular image with annotations. Feature is the raw image. Annotations is the markings, masking on top of the image. Bounding boxes, segmentation masks, these are all called annotations. And you can see here how this guy is using something called encode to annotate the images. This is how people used to manually do it. They used to draw boxes around the images, and they used to write car, and they used to drag boxes around the building, and they used to write building. This is how annotations usually work, and it used to take a lot of time, but nowadays it's not. And as you can see, there are different ways to do it, and I'll talk about them. There are different ways to annotate an image, and these are some of them that you're seeing here. Yeah, you can see here this, I mean, automatically here, this is automatically doing it. This is a person and this is a bicycle, that it is being outlined and annotated. This all is what's stored in the dataset. You can see here. All the boxes that you see are called annotations. The image itself is feature. Yeah, any doubts still here? Okay. So some of the annotation formats that you will encounter in your lifetime, sorry, not lifetime, is in your career probably, are these Coco JSON, YOLO text, and Pascal walk. So when you save your annotations, they have to be in a format the model expects. You will encounter these three in the main formats in the wild. Let me talk about all three of them. Coco JSON. This is used by Microsoft Coco. This Coco JSON. It stores everything in a single nested JSON file containing images, annotations, and categories. Coco JSON is incredibly versatile, supports both bounding boxes and complex polygons. How the JSON format looks and all, I'll give you an example in the project, or I will show it in the internet how it looks. But I'm just letting you know, like this is used by Microsoft, incredibly versatile, supports both bounding boxes and complex polygons also in CocoJSON. In YOLO text, used by the famous YOLO models, there is something called YOLO models in internet that you can use for computer vision. All of my projects are using YOLO only. Very easy to use. It creates one simple text file per image, logging the class ID and the normalized coordinates. So how YOLO text works is like, this is the image, right? This image name will be stored, and the coordinates of the image, I mean the image will be divided into x-axis and y-axis. So from point here to here, from here to here, from here to here, and from here to here, this box in that image is a human. This box with this perfect coordinates is a dog. That is how YOLO remembers. YOLO text remembers in this way, and it's great for fast object detection. YOLO is one of the fastest object detections out there. YOLO, one text file per image, 1000 images, 1000 text files. Next is XML format. For XML formats, Pascal is one of the famous one. An older form, this is somewhat older also, an older format that creates one XML file per image. You will see this a lot in old companies, old legacy pipelines. You will see Pascal walk XML. So all these three are doing the same things if you understand. Each image one JSON, each image one text file, each image one XML file, but the formats are different. Here it is doing in JSON, here it is doing in text, here it is doing in XML. The formats are different, but what they're doing is the same thing. And in you may also come across a few problems where your data is in the wrong format. For example, your data sets are not in JSON format, text format, or walk XML formats and all, or else you have to make your own data formats. You can use tools like RoboFlow or Label Me to Coco. You can use both of them to convert between formats. For example, you are using YOLO Abba, you are using YOLO model, but your company is giving you a JSON format. YOLO models don't take JSON format, they take only YOLO text. Okay. So when your company is giving CocoJSON, but if you are working on YOLO models, simply you can use RoboFlow or Label Me to Coco to convert those formats. You can convert from JSON to text, text to XML, XML to JSON. You can convert into different types. And if anyone of you are wondering what is this BN Srino thing, our friend gave us a GitHub. Let me also show you that. I saved that GitHub link. Yeah, on Thursday I was going through this repo. This one. Our friend shared me this repository. Even I took the same reference. So while taking the reference in the PPT presentation time, I have included this GitHub thing also. So here in this repo, the annotation tool video, this one I guess, yeah, in this annotation tool, when I've gone through this entire code, they're using CocoJSON by default. It's exporting to CocoJSON. I'll share this GitHub link as well. Yeah, I'll share it with you. I think I can share it now itself. Thank you, Kom. If you wouldn't have bring it, I wouldn't have brought this computer vision at all.
Yeah, no, I think I really wanted, so I was like, thank you. Because a lot of people kept asking when I said I do a lot of imaging, image analysis and all. And it was a lot for me to like kind of like follow through. And Monesh, the conversion formats is the RoboFlow converts between like text to JSON or like JSON to text. So is it vice versa? Those two formats, like between any formats, it does,
Uh,
or should I look at a?
I honestly don't remember.
Okay, okay, I'll look into it.
Yeah,
Yeah.
yeah. I'll check now. Converts. Oh yeah, it converts from RoboFlow converts JSON to text.
Yeah, thank you.
Yeah.
Yes, I.
So this is thing. Yeah. So how do you work on this OpenCV projects? You don't always have to start from the scratch. There is a massive high quality public data sets available for science readily in Kaggle, Hugging Face, GitHub and all. There are a lot of public data sets available. Like in medical pathology, you have cell annotations and lot of data sets. Remote sensing, biology, ecology, industrial, generical benchmarks. You can also make your own custom data with your own for your own business as well. Yeah, you can pick any of these data sets and you can start creating a project on it. Even Google Lens is one of the best example I can give for OpenCV. It was so well trained. Google Lens, if you have ever seen, you can just scan the plant. Recently I went for buying few plants for the indoor house decoration thing. So I honestly I don't know nothing about plants, like what types are there and how this and that and all. I just used Google Lens there. I opened Google Lens and I was scanning each and every plant, and I was finding out pros and cons, whether I can keep it in indoor or outdoor, and it was giving me a very precise answer in a very fast pace. So that is one of good examples of use case of OpenCV. Yeah. So let me talk more about this image and before that, any doubts still here? Okay. So this is where the magic happens. All the project that any OpenCV project that you take, the magic happens in annotation itself. We are going to look at how we actually label our data, moving from tedious manual work to automated AI workflows. So there are four main ways to annotate an image. One is called bounding boxes. I mean the same way. Here you are seeing, right, object detection, image classification, segmentation, instance segmentation. These are segmentation types, and these are annotation types that I'm talking, but they are so similar. In segmentation, again, you have different types. So the one that you are seeing here is segmentation types. Image segmentation, instance segmentation and all. So yeah, the four different ways you can annotate an image is bounding boxes, the most commonly used method. Rectangles around the objects. It's the fastest method and what we use for basic detection. Example, the one you are seeing here. Put a rectangle around an object, just give a name to it, over. That's all. Done. Next is segmentation masks. Segmentation masks is like tracking the exact pixel outline of an object. It's highly informative but incredibly tedious to do by hand. all of the latest AI models that you are seeing, like your pixel, if you are editing your image in a pixel mobile, you will see segmentation masks. In Apple phones, you will see segmentation masks. So what happens is, the best example is the one you are seeing here. The object, instead of rectangle, in the problem of rectangle, I'll tell you, you see this grass, right? The grass, the unnecessary grass around and the ground, that also being detected as a human. That pixels are detected as human to the model. So which creates a problem. But with segmentation, what happens is only what is needed is being given to the uh, model. There is also something called, I mean, it's not given here in this website, but personally, this is something I know. There is also something called multi-level segmentation masks. What does multi-level segmentation masks do is, the same guy is carrying a bag, right? A school bag or something, and a water bottle and something, this one. So you can also name them. You can say that this complete pixel is a human, but these pixels are a bag, these pixels are something else, something. So that is called multi-level segmentation. This is a normal segmentation that you are seeing, where it generalizes. It generalizes the entire human body. And bag also will be a part of it. It is incredibly informative, but very hard to do by hand. And olden days, they used to do it in this way. Next is classification labels. Classification labels is simply tagging the whole image. For example, this is widely used in cat, dog, disease, no disease, infected, not infected, healthy cell, bad cell, these kind of images. So you take a complete image and you give a name to it. You take a cat image, just give this is cat. You take dog images, say this is dog. This is called classification labels, which you have already done in deep learning class. And the next one is key points and landmarks. This is widely used in your Google Maps. Marking specific anatomical points like joints or cell centers and all. Key points and landmarks, best example I can give you is, I can visually show you. It's not working yet. Let me check this. Wait, it's not working. I'm not sure why it is not picking up, but I think you got my gist what I'm trying to say. So in the beginning classes, when I was using this rusty robot thing and this alien things, right? These are examples of key points and landmarks. So what happens is, in the image, in my image, using my camera, uh, it identifies my eyes, it identifies the way I move my jaw, it identifies how I move my eyes and all, and then it tracks them by using this key points and landmarks. So there is no static point, but it moves along. So specific joints, cell centers, as an example that I mentioned here, they get tracked. That is an example of key points and landmarks. And also Google Maps, what it does is, whenever you take a photo, with your Pixel mobile or your Apple, in the metadata, the location where you have taken the image, what time you have taken that image, that also will be stored. That also acts as like a key point and a landmark. So these are all the 4 image annotation types that we have. So any doubts still here? So in today we will be focusing more on bounding boxes, boxes and masks. These are the two will be heavily depending on, because these two are classification labels. We have already seen it in deep learning. That's one of the example of cat, dog, the t-shirt and all. Key point landmarks are hard to do because they need a tracking, like a live track and all. Bounding boxes and segmentation marks are much more easier for a project. And manual annotation platforms. If, for example, Monesh, I don't want to go with automation. I want to go with manual annotation. I want to do it on my own. If you're thinking in this way, you can use something called label. These are all the things that I found in internet widely used. Label LMG, label image. It's free, open source, widely used for YOLO and Pascal. It also has a desktop app. And it has nearly like 17k plus GitHub stars that I've seen. Very good. You can use this, or else you can use something called Label Me. This is also free, classic, open source, and you can run from desktop. And it's great for segmentation as well. Next is CVAT and RoboFlow. These two are more modern and built for a team's usage, not for individual. But if you are working as a team friendly, these two are very good, RoboFlow and CVAT. If you are into pathology is in the sense, I said right, this one. Pathology is this one, key points and landmarks. If you are working something on pathology or QPath is specifically designed to handle massive whole slide images. Any images that moves can be handled by QPath. But doing this purely by hand takes hundreds of hours. Yeah, it takes hundreds of hours, if any of them. So this custom tool, like that I have seen in this thing, video for annotation tool, I've gone through the entire code. It took me a few hours. I have spent some good amount of time in all these files. I'll be sharing with you. So in this, they have automated using custom tool. They have automated the annotation process using a custom tool in this. So yeah, you can go through it. I'll share it with you. And the project also will be using similar thing of what they have done in our project, CocoJSON. Why we are using Coco? Because they are using Coco. Again, I'm saying the entire class was designed around these all files. I've taken this complete repository as my reference point, and based on that, I've designed this presentation and my own project. So whatever they are doing, we will be doing similar kind of thing. They used a custom tool for automation. We will be using similar to that. And for automated annotations, even in this repository also, they have used something called grounding dyno. Grounding dyno is the zero-shot open vocabulary object detector. What does that mean? It means you don't need to train it on your specific classes beforehand. You don't need to do any kind of training. You give an image, you give it a text prompt like mitochondria or nucleus or something, and it uses something called BERT text encoder. And also it uses something called a swim transformer. I saw somewhere. In this one, somewhere I saw a swim transformer being used. Not here. Swin. Yeah. There you go. Swin. I remembered seeing it. Yeah. So there is something called Swin transformer, SWIN. So Swim transformer used to fuse the image and text features together. They have used it. It outputs a bounding boxes with confidence scores on top of the images. It looks like it's practically magic, but it accelerates your labeling process. These two, and we will be using that in our project. Whatever the project that we are going to do, we will be integrating them. So grounding dyno is used for automatic object detection, automatic annotation, and also they are using SAM2. SAM2, once grounding dyno gives us a bounding box, we can pass that box directly into SAM2. SAM2 is nothing but meta segment and anything model 2. SAM stands for segment anything model. SAM stands for segment anything model, and it's again, as I said, it was from Meta 2024, latest, very latest. And SAM2 treats the bounding box as a prompt. It looks inside the box and instantly generates a pixel perfect segmentation mask. So again, I'm repeating, grounding dyno creates the box, creates this rectangular box, grounding dyno. What does this SAM2 boxes do? It will pixelate. It will pixelate to the right mask. So there, your rectangular boxes, here it is being pixelated. So first step, second step. Yeah, after that, dyno detects the objects via text, SM2 segments the object via this dyno box. Then we export the masks in some milliseconds of time. It just takes milliseconds. Yeah, now we will be doing some small lab work. Everyone, you open this repo, go to video 4, video annotation tool 4.py. Here we'll be doing a small exercise. What if you don't want to download the entire repo, you can also download the individual files. You can just download a raw file. I paste it in desktop. I go to Colab. Will I be able to upload? No. I have a way to upload Python into Google Colab. Yeah, this I think. Yeah. Change the runtime to T4 GPU. I'll also share this IPynb file. So what you have to do is, yeah. So you have to run this. Or else, once you open that file, annotation tool v4.py, first I'll tell you what the tool does. The tool will combine everything we just talked about. You can draw boxes manually, but when I want you to try the AI assistant mode, type a prompt, let Dino and SM2 propose the annotations, and then simply review and you accept them. Run the script, load 10 of your own images, use text to prompt to auto annotate, review and correct them, and export them. I did not run it in Colab till now. This is even my first time running in Colab. I ran that Python file before. Let's run like this and see.
I actually tried this, Monesh. I mean, running through the Colab,
Mm-hmm.
but I think there is this the annotation, like the GUI interface that is incorporated, which is PyQt5. That did not let me run through the Colab because that particular one has to be installed on the computer, is what my understanding is.
Okay. Then
Because you see, if you see that there is a PyQt5 particular library.
yeah, same issue here.
Yeah. So that is why in the beginning I asked if we can do it on the Colab because I could not crack that running through the Colab.
We will try. If not, I'll switch to
Okay.
local. Oh, wait. It did not convert properly. I see that. What is this thing? Functions are not properly converted, so this website is bad. Let's try this. It all says it's invalid. You know what? Instead of doing this, just copy everything. So I'm doing two things here. I'll tell you what is going on. One, I'm not doing it in local in my Python. I mean, in my VS Code environment is not all of our system are in the same level, and I don't think all of you have all the libraries and the environments already prepared for it. That is one thing that I'm stopping myself to run it in the local. The second, Colab is not allowing me to do. I mean, it's a PVR file. I'm trying to convert into IPYNB, but the online conversions are not better. So what I did is a simple hack that I usually do. Whenever you want to make a Python file into IPYNB file, just copy the entire Python code and put it in one cell, in one IPYNB cell. That usually works for me. It does the trick, but I think it should work now. This is one pyqt5 error. Let's install it. This is not at all recommended, but I'm just doing. You should not paste that much amount of code in one particular cell. Even this also takes some time, because it has to, even for small error, it has to read the entire code. Or else I can just copy this, right? I can copy this, stop this, go to the top and replace it. I think this should work. Runtime to T4. Manage sessions. Remove this one, close, and run all. And yeah, while this is going on, I just want to show my new find to you. That is called Cline. CLINE Cline. So if any one of you don't want to pay for subscriptions to AI models like ChatGPT, Gemini, or Claude, but you still want some AI to work in your code, like what Claude does, Cline also can do the similar kind of things. But as you can see here, they cost $0. It's completely free. It's a new thing that I found in the extensions. I was using it for quite a while, and it is good. Klein is so good. I still have this Claude subscription, so I'm using this, but I'm thinking of stopping my subscriptions as well, because Klein is working very well for my use
Is
cases.
it very specific to like coding or in general?
It is giving me generalized answers also. Like if I ask anything unknown fact, it is answering me. But
Okay.
yeah, I'm mostly using it for coding.
Okay. Okay.
Klein. You can go to extensions, and in the extensions search for Klein. Yeah, this is the one. It's recently getting popular. Completely free app. I don't know how long this is going to be free, but for now it is completely free. And Klein also has their own models, and also it has capability of you uploading your own model as well. So you can also upload your own. If, for example, if you have a Claude model in your laptop which is downloaded offline, you can use that as well. These and all the external apps that client can connect to. For example, if you want to do some API testing, client can do it for you. It can automatically connect to Postman API, and it will check for all the backend stuff. It tests it and it gives the results. Yeah. Yeah, this is where you can pick up the models. Cloud Opus 4.7 is also available. And one more. I mean, it's already done. I'll upload it to Google Colab. One more funny extension. If any one of you are using Claude, I removed it. Yeah, I removed it. It's called Pixel. Pixel agents. So what pixel agents do is, if you are using Claude, and if you are using multiple AI agents at the same time, that is how usually I do. So I have multiple agents. Like one AI agent will be working on the documentation part. One AI agent will be testing. One AI agent will be working on the front end. One AI agent for the back end and all. So pixel agents will see if any agents are working in your computer as of now, and in the terminal it creates a mini office. It creates a mini office in your terminal. So what happens is, when you create an agent for coding, let's say a person will be shown as typing in the computer. If you create an agent for doing the documentation, you will see one person going to bookshelf and he's reading something. So it's a fun way of seeing what agents are doing. You can maintain a mini office in your computer. So that is this pixel agents. It is also gaining popularity. Okay, it is created. Now let's go and check. First of all, I'll move it to trash. Upload, browse, desktop. What's it's named? Video annotation tool. I think this is the one. Yeah, let's run and see runtime. Or else, yeah, instead of wasting time, I'll skip this part because I myself have to make sure first it works fine. Then I'll show you. Maybe in the next class I'll bring this up. A lot of, I mean, still it is working, checking and all. But yeah, don't worry. I'll show you how to annotate, how annotation works. Because in our project also we'll be doing it. And before we go on to the training, we have to talk about quality control. Quality control is nothing but how good your annotations are. A fast model means you can generate garbage faster. Remember it. When you have a faster model with bad annotations, you are just generating garbage. So watch out for missing annotations, sloppy, loose boxes, or class imbalance. Some of the best practices are always writing a labeling guide for consistency, setting strict IOE thresholds for your quality checks. As a rule of thumb, aim for at least 200 high quality annotated instances per class. What I'm saying here, when I mean 200 high quality instances, means at least you have same class 200 images, like for cat 200 images, dog 200 images, for bag 200 images, humans 200 images, at least high quality, before you attempt fine tuning. And this line, augment minority classes like flipper, rotate, color jitter and all. So even minute things also, if you automate, it would be good instead of all putting it in the same class. Example, this one. You should annotate this is a bag, this is a human, and this is something like a tent or something like that, a water bottle and all. If you don't minimize your annotations, that also makes noise. So before going to data training, before I talk about this, any doubts still here till this moment? Okay, I did not hear any doubts. So before we actually start the project, I'll talk about training and evaluation. We in PyTorch, in PyTorch, yeah, I remember. Yeah, in PyTorch, data flows into the model as pairs. We'll be using PyTorch for our project as well. In PyTorch, we'll be sending the data flow into pairs, in as pairs. One is features and the other is targets. Features are your images converted into mathematical tensors, normalized and heavily augmented, flipped, cropped, recolored to make the model robust. This is what we have done in tensors, deep learning class. If you remember, we have used PyTorch and we have converted this images into mathematical tensors. I've told you, like, every image can be converted to some tensor. So we'll be same thing. We'll be using image tensors here. Targets are your annotation tensors, the bounding box coordinates, class IDs, and all. A DataLoader packages these into batches and feeds them to the GPU, so the model can learn the relationship between the pixels and the labels. So that is what training we will be doing in the data pairing section before the training. So we'll be combining our images with the annotations mathematically. We'll be doing it mathematically because ML cannot understand images, it can only understand numbers. And this is how we'll be sending images data plus the targets data. Targets will be the annotation. Any doubts still here? Okay. So I'll just talk about this one cell and then we'll be going for a break. While grounding Dino is great out of the box, fine-tuning it on your specific scientific domain makes it incredible. And this is, I've taken a reference from video 5. We freeze the heavy swing backbone and only update the later layers. We'll be using something called Adam W optimizers for using fine-tuning grounding Dino. And for doing this, you need at least equal or greater to 16 GB of VRAM. This is the point that I thought, okay, let's not do it in local. This is the reason I'm not running the code in local, because now I don't think all our system will be in the same thing. So that is the reason. Yeah, let's take a break. In the meantime, I'll figure this out. And we'll meet after the break and we will see. Anyways, the project which I designed will be in Colab only. The entire thing that I've designed will be only for Google Colab. So even if I missed out to run this, I'll show it in the project.
Yeah. Thank you, Monesh.
Yeah.
We'll be back.
See you after the break. Yeah, thank you. So yeah, welcome back everyone from the break. Oh, I took extra 5 minutes. Okay. So let us start. I mean, in the next class also I'll try to get this working, and I'll show you some more the other way in Google Colab. I was not prepared for that. The time is also short for me. Let's do the aquarium object detection project. So today we are going to build a computer vision model from scratch. We will not going to take any help. We are going to build a computer vision model from scratch to detect and classify aquatic animals. We will be using a Kaggle dataset containing 638 images. There will be 7 classes in it and originally formatted in Cocoa format, Cocoa JSON format. By the end of this session, whatever the time we have, we'll try to complete it. If not, we'll complete it in the next class. Whatever we can, we'll try to do it in this class with the time we have. So we'll be, as I said, our goal is very straightforward. We will find the fish, penguins, shark in these images and draw bounding boxes around them. We are going to fine tune a YOLO V8 nano model, which is incredibly fast and perfect for a free Colab GPU. To do this, we will be loading the dataset. We'll be downloading a dataset from Kaggle. This is the link that I've shared. It's a Kaggle dataset link. Yeah, this is the dataset I was talking about. It has 3 directories and 3 files, and each directory will have two folders: images and the labels. Images are the actual feature images. Labels are your annotations, targets. I said right, every dataset will have 2 folders: images and the labels. So we'll be using this particular dataset. We'll be loading it. We'll be exploring and visualizing the annotations. We convert those labels from Cocoa model to YOLO format. Why? Because as I said earlier, you cannot use Cocoa for YOLO models. YOLO models, you have to use only YOLO format. So we'll be converting from Cocoa to YOLO. And then we'll be pairing the images and the feature labels. We will train them and then we'll be evaluating the results. That is what our 5-step CV pipeline is going to look like. Any doubts still here? Anyone? Okay. So take a look at the data set. We will be working on the aquarium combined data set. It is already split nicely for us. 440, I don't remember, 448 I guess. Is somewhere written. It's not written here, but I know from my mind 448 images are for training, 127 are divided for the validation, 63 around are for testing. One thing we have to pay close attention is to our class distribution. Here, you once look at this class distribution. Sorry, yeah.
I don't think you're sharing your screen.
Oh my God. Sorry. Yeah, thank you. Thank you. Let me go back a little bit. We are doing the aquarium object detection project, 638 images, 7 classes, Cocoa format. And this is the 5-step pipeline I was talking about. Actually, I think I made a mistake. This is not the data set, I guess. I have few data sets in my system. I think I gave you the wrong link. Did someone join? No.
it's me. I had an issue. Can you send the link again? Because I had to exit and rejoin
Yeah,
for the
sure.
chat. Thank you.
A collab, dataset link, right?
Link also if you have sent
Okay.
that. Yeah, thank you.
Something is not right. This dataset contains 638 images. From the 638 images, how can there be 2669 fish? Multiple. Okay. Got it. So I shared the dataset link. It's the same dataset as before that I've shared. I've shared the collab link also. I'm sharing the link. Yeah. So yeah, this is the dataset. I just got confused for a bit on why there are 2669. I just forgot to see this line. Here what this line says is most images contain multiple bounding boxes. In the sense, there are as I said, there are only 639 images. I mean 638 or 639. How many? 638, yeah. There are only 638 images, and 7 classes. 1, 2, 3, 4, 5, 6, 7. But each image has multiple fishes. That is what this class mean. Like for one image can have a shark, puffin, and stingray and all. So each image can have multiple classes. So that's where I got confused for a bit, like why there are 2669. But yeah, now I got it. So each image has multiple fishes in it. That's why multiple. The multiple, like jellyfish is 694, but there is only 638 images. So it is multiplied in different images. And you can download this, or you can use the code that I'm going to show you getting the collab. Getting this data set. You can just copy this, go to here, paste it, and run it. Okay, it got downloaded. It's in root. Always it takes some time. Yeah. So yeah, you can see here, these are the images that we are dealing with. We have multiple images, different types of images and all. You can see all the different types of images we have. And one interesting note here is, if I you see this image, right? The same thing will be in the label also. You see image 2289 JPEG JPG, image 2289 JPEG JPG. I mean the file name also will be similar. It will be the same for the image and for the annotation. So let's see how the image and annotations are. This is the image. This is the image, and this is its annotation. So this is class 3 in this coordinates. This is the coordinates box, that the rectangle box, and this is the class it belongs to. You cannot understand what it means, but the model understands it better than us. So these are the images and these are the coordinates and the class types they belong to. You can see more about the dataset from this given link. Let me verify the structure. This is the code that I have made, and this is used to verify the structure of our dataset. Why it says not found? It's there, right? Kaggle. Kaggle input. Kaggle input aquarium dot. Oh, there is also aquarium pre-train. Okay, let me fix it. Yep. So there were 448 images of train, 127 images of valid, and 63 images of test. We don't need this code anymore. Okay. Labels, they're in the format of .txt. Okay, yeah, I hope all of you have got the data, looked at the data. Mm, this is not required. I'll tell you what is going on. This won't work for us. This code and this code won't work for us because I mean when I was looking at the data set, it was in Coco JSON format. I think I looked at a different data set on that day. This is in YOLO format. How do I know is by going here, and when I looked at the extensions, if you observe, this is in JPG format and this is in TXT format. And if you remember, TXT format is not Coco JSON, it is in YOLO. I'm just wondering, on Thursday I think I saw a different data set altogether. Underwater object detection, Coco. Yeah, I don't know from where I've seen that data set then, but yeah. So this code is used to convert Coco formats into YOLO formats. I mean, you can use this code to whenever if you want to convert from a Coco to YOLO. This is what the code you will be using for. This code. Yeah, this is also for the same. If you want to explore any Coco annotations, this is the code that you will be using for. But right now, our data set is so good, it is not in Coco format at all. It is in JSON format. Sorry, it is in text format. Text format means your YOLO. It is in direct YOLO format. So since it is in direct YOLO format, you no need to convert it from Coco to YOLO. So that is one burden that got reduced. And most of the data sets you'll see is in YOLO format only, text format. I think I saw a different version of this file, this data set. Every data set will have multiple versions. The author will be updating the data set. I think I saw an older version on that day. An older version might be in Coco format, and the newer version they have converted it to text format. So that is the reason I got text here. So this code is to just validate how many images are there, how many each category things are there. And this is to convert, I mean, not the word convert. For YOLO architecture, YOLO needs a .yaml file, .yaml file that tells the YOLO architecture exactly where our images live and what our 7 different classes are. So for that, we need to convert our text to a .yaml file, and that is what we have done here. Let me also show you how the YAML file looks like. Yeah, this is our data.yaml, and we will be using this instead of the aquarium yaml.save. This makes more sense. So this is also is coming from the dataset. This is something not I have created. You see data.yaml class labelings in YOLO format. So they have made the entire dataset so suitable for YOLO that I no need to do anything. Already the dataset is in YOLO format or YOLO model format. So this cell is also not required. We'll be using this data.yaml. Copy path. Yeah. So just to cement on what we did, input X are the images themselves, and we also call them pixel tensors, and they're resized to 640 and 640. Usually this is the code to do that here. This is the code to convert your bigger images into 640 into 640. Monesh, why 640 into 640? Because 640 into 640 is the minimum pixel size that YOLO requires for training. So that's why we convert our images to 640 into 640. But already our images are converted, the dataset images are converted. So for every image we feed the model, we feed it with the matching text file, so it can calculate its loss and learn. Every image we feed, we also send its label data also, so that it understands how many images are there in, how many labels are there in a single image. And for that, this is the code. Same thing. Device is CPU. Oh yeah, I forgot to convert to GPU. My bad. So I'm converting it to GPU and rerunning it. While it's running, I'll tell you what this code is for. So we initiate YOLO V8N, this one. We use this YOLO V8N. The N means nano version. So we are using YOLO version 8 nano version of it. It has 3.2 million parameters and it is highly efficient, YOLO V8N. The dot train method here, the dot train method handles the heavy lifting. We pass our YAML file, we set it to 50 epoch, and we use batch size of 16, and we also enable augment, so the model sees flipped and color adjusted version of our images. So the same image, it will be flipped and it color also will be changed here and there, but still we are providing different angles of the same image also for training, and this prevents overfitting. Once training finishes, model.val, why it's not going? Yeah. Once the training finishes, model.val runs against our validation set to give us preliminary metrics. This one, model.val. But why it's not running? Okay, I might know why. Yeah, it's running. The training is going on. Okay, now in this class I cannot run up to 50. I'll run 10. I'll stop the execution and I'll run only first 10. Again, I'm saying YOLO V8N is the algorithm that we will be using. And we just like how supervised unsupervised learning we have done, we are also putting some parameters here, and for after that parameters and after the training we are checking the metrics. Model.val will automatically give you the metrics of putting it on the validation set. This is currently I have given 50 approach, 50 times the iteration performs, but in this class with our time I cannot do 50. I'll just do it because 50 minutes it takes up to 25 to 30 minutes. So I'll just do it for 5. The precision and recall will be bad, but you do it for 50. Let it run for 3 more times. Okay. So you see that we got some metrics. Uh, Runnable rate, yeah. So right now you know about precision and recall. Precision we got something around 0.5. Recall we got around 0.4, which is bad. I know, but we have done only epoch 5. So for epoch 5, this is what we get, and this map at 0.5 and map 0.5 to 0.95, these are the two important evaluation metrics used to grade object detection models like YOLO. They tell you how accurately your model is finding and drawing boxes around the objects. To understand these two numbers, you first need to understand the core concept that they rely on. They rely on something called IOU, intersection over union. What is IOU, Monish? IOU, key evaluation matrix. The first one is IOU. Before a model can be scored, we have to define what a correct guess is. IOU measures the overlap between the predicted bounding box, where the model thinks the object is, and the ground truth box, where the object actually is. An IOU of 0.0 means the boxes don't touch at all. Then an IOU of 1.0 means the boxes overlap perfectly. Monesh, what are you talking about? Let me open whiteboard. This is the trainer. Okay. This is the validation. In the train, we have an image, a person image. And we have a rectangular box around him. Okay. Something like this. Okay. Now, the same thing. Well, in the validation, I mean the same image when we are testing, when we are doing the valuation, the algorithm tries to draw the box. So let's say it has drawn the box like this, something like this. Okay. Then it will compare both the images, whether the box is perfectly the same like this one or not. So if the boxes are not matching at all, then you get a score of 0, an IOU of 0. If the boxes are matching perfectly, overlap perfectly, then the score is 1. An IOU score will be always between 0 and 1. That is this IOU. 1 means perfect. Greater than 0.5 means correct. Greater than or equal to 0.75 means strict match. If they are not at all matching, it will be 0. And let's break up this MAP scores, this MAP thing here. So what is this MAP? MAP means mean average precision. Think of this as your model's overall accuracy grade, average across all the different classes it is trying to find. At 0.5 here, map 0.5 means this is the difficulty setting. It means the model only needs an IOU of 0.5. Only needs 0.5. A 50% overlap with the real object for it to be counted as a correct detection. So 0 at exactly 0.5, the average is 0.482. The more the average, the better the model. That's what I'm trying to prove. The more the average, the better the model. 0.482 means 48. The model scored 48.2%. So what does this mean? When graded on somewhat forgiving curve, only requiring a 50% overlap, your model successfully detects object at 48% of the time without making any false positive mistakes. So 48% only your model is correct at identifying the objects. Monesh, then what is this? Map 0.5 to 0.95, the value is only 0.266. This is the ultimate strict benchmark. Ultimate strict benchmark in the sense, in 0.266, there will not be any false positives. Or most of the time they are accurately good. And the value is only 0.266. 26% of the time it will accurately identify the object with the overlap. There will be no false positives at all. So that is what MAPs mean. So 0.5 to 0.95 means the box it has drawn, right? That was so accurate between the original and the what model has drawn. 0.5 means only 50% match. 50% match is good. More than 50 is very good. 100 is excellent, perfect. Anything below 50 you should not consider. And you already know what is precision and recall. So any doubts in this? In your metrics? IOU stands for intersection over union. The box, the rectangular boxes, how well the rectangular boxes are mimicked is your IOU. Mean average precision MAP means this IOUs we will be taking an average across all the classes. If you take the IOU average for all the classes, you get MAP. MAP 0.5 means 0.5% of the box match, exact box match. 0.5 to 0.95 is 50% to 95% of match. Any doubts still here? Okay. So training is done. After the training, yeah, this is done. After this evaluation, I mean visualizing, just plots. I'll tell you what is going on. Yeah. So what I have done with this code, let me tell you. Let's go like line by line. So after the training will create a .pt file to use. .pt. You can also see it here. Optimizer striped .pt, validating on the best .pt, a pt file. So we load our there is a full form for this PT. That is not coming to my mind. Let me ask here. PyTorch. Yeah. PT stands for the PyTorch model file. So whatever the training happens, the training will save it in a .pt file, and that is why you see here in the console that it says like all the pt file being used. And you can also see it in the content runs in YOLO 8 and 4. You will see, where is the pt? Yeah, best.pt, last.pt, and all. So we load our newly trained weights from best.pt. We grab the 4 images from the test set, any 4, and pass them to the predict method. We use a confidence threshold of 0.35. So anything that has confidence greater than 0.35, we draw the box, meaning the model will ignore any predictions that it isn't at least 35% sure about that image. We then iterate through the result.boxes. We extracted the coordinates and draw the model predictions over the image, so we can visually grade its performance. You can see here we have taken first 4 images of the test set, and in this image we have drawn the box. This box, it says here, see, jellyfish is 0.61, means 61% sure that it is a jellyfish. This is 35% sure it is a jellyfish, and this is 92% sure it is a starfish. Something here also, shark, fish, shark and all. Here there is no detections at all in the second image. Why? Because and the least that you will be seeing here is 0.35, that is the jellyfish 35%, and the threshold is also 35, and IO is 45%, means 45% it has to match perfectly. Yeah, any doubt still in this? Okay. Yeah, I already told about the metrics to you. This is a small chart that we can make out of. So this is the 0.5 threshold line, and you can see string ray. I mean the precision rate, the average precision rate is 0.531, 0.480, 428, 0.079 and all. So the highest that our model was able to identify is a jellyfish, because the average precision rate is 0.793 with epoch value 5. With just epoch value 5, it was 0.793. My guess is with epoch 50, it will be at least 0.9. And these 3 will also cross 0.5. I doubt Puffin will be crossing 0.5 at all, but rest of all will be crossing 0.5 with epoch value 50. You can try with epoch value 50. We have done it with 5. So we are extracting in this image, we are extracting the average precision of IOU to be 0.5 for each specific class. And as you run this, you will notice that fish and jellyfish, these two, score very high, while starfish, examples like not puffin, while puffin scores much lower. Recall our class distribution that I said that we only had about, and this is also completely dependent on where is the chart? This chart. It is also highly dependent on this chart because we only had about 284 puffin. So maybe that is the reason it was identifying less. But if you take starfish, starfish was the lowest among all, 116. But starfish identification is much more. Starfish is good, 0.480. But for some reason, it was unable to identify puffin with only approach value 5. If you increase the approach value, puffin also would be identified better, in a better way. And this, I've done this graph just to prove that data balancing is very critical in machine learning. And the model doesn't have enough examples also for starfish, especially because starfish is only like 116 times, and starfish has very low examples, but still it was able to get to 0.4 with approach value 5 again. So yeah, that is all I have. These are the metrics I want to talk about. But I think I'll continue computer vision in next class also. Main reason is I want to show that GitHub thing that our friend shared, that GitHub repo, but I'll find a way to run it in Google Colab. Yeah, I'm share this one more time. So yeah, if anyone have any doubts still here, let me know. I'll just give you a recap. We started a project on computer vision for identifying and classifying the images with annotations. That is what computer vision does. Computer vision ends with annotations. It is not for predictions. It is not for what do we call classifications and all, because computer vision plus classifications and predictions give you deep learning. That is what we have done in the deep learning class. We have taken the images and we have classified them. It again becomes a deep learning class if I keep on go forward. Computer vision starts at the raw images and set the annotations. That's all. These are the only two aspects that computer vision does. It identifies the images and it annotates them perfectly. How well it is annotating is where computer vision talks about. And this is what a simple computer vision project looks like. This is not required at all. This second step. You can just do these three. So we downloaded the Kaggle Hub dataset. We loaded into the algorithm called YOLO V8N, and PT stands for PyTorch, and we have trained the model. After training it, we have done the validation. We got the metrics, and after getting the metrics, we predicted those. We predicted by using that model on the test data, and we were able to get some test data annotations. We have validated them with some. We got some accuracy, and finally we have run it across all the classes with our test, and we were able to get our average precision for every single class. That's all. That is where computer vision ends. Anything extension to this, like predicting, classifying, you again go to deep learning. But yeah, this is the overview of computer vision, but there are a lot of things inside computer vision. And in next class, I'll try to get that repo running with this one, that BN Srinu's repo. I'll try to make it run in Google Colab. I was able to run it in local. That is how I understood the codes. But I don't think all of you can run it in local. I'll try to get it up and running in Google Colab by tomorrow. Yeah, any doubts, anyone from the project that we have done today? The aquarium detection, object detection project. It's very simple project, just like four cells. 1, 2, 3, 4. Yeah, just 4 cells of code. And one more thing, I'm not delving more again into this figax, bars, ax dot set and all. This is the code we are using from, I think, class 3. The same code. In every project, you will see similar types of code. So I'm not repeating them again and again. Only these are the new things that we have done using YOLO V8M. And please run it with 50 and see if you are able to get it good. Just put approach value to 50 and run it. It will take 30 minutes of time, but you will see it. It is worth the time. You will get better results. So yeah, any doubts, anyone from this class, from this project?
I'm running it for the 50 epochs. It's still running.
Okay. So yeah, that's all for today's class. And in meantime, if anyone have any time, just go over this repo that our friend shared, because tomorrow I'll try to get it running in Google Colab. We'll try to make this work and I'll try to make you run it. And I'll tell you what is going on in this, all the things. Yeah. So yeah, that is all for today's class then. Love you all. Take care. Go through this project one more time. If you have any doubts in the project, also let me know. Yeah, see you all in the next class then.
Thank you, Monesh.
Yeah.
See you.
See you. Take care.